All right, let's look at this lemma. It says this, linear transformations preserve non-collinearity, right? So which means that if you take three known collinear points, it will be mapped to three known collinear points. So we cannot make non-collinear points turn it into collinear points, right? So proof is a little bit of tedious, so I'm going to give you a sketch of the proof. All right, before we get into the proof, we want to review postulate of Pasch. All right, it says this. If you have a triangle ABC, and D is a point between A and B, right? Then if you have a line going through this interior point D, and the line does not include the A, B, or C, then there are two possibilities, right? So we know that if you have a line going through D, then it's going to either intersect segment AC, so which means that there's going to be an intersection here. Let's call it E. Or another possibility is it's going to always intersect segment BC. Not always, or it's going to intersect AC or BC. So there's going to be intersection point, let's call it F. Right? So this was the result of post-zero Pasch. Right? We're going to use this to prove this lemma. Right? So proof is by contradiction. So linear transformation preserve non-collinearity, right? So let's assume that if they don't, right? So let's do this. We say let's choose any linear transformation. So choose any linear transformation. So I'm going to just say linear transformation f, right? Then, so we're going to assume that this linear transformation sends non-collinear points to collinear points. So we say assume the opposite of what we want to say. So let's say f does not preserve non-collinearity. Right, so which means what? So which means that there is going to be non-collinear points. Let's say call it A, B, and C, right? In the plane P. Let's call this plane P, right? So we have three known collinear points, so we can say something like A here, and then you have a B here, right? So maybe C is over here, right? So you have a non-collinear point, so we can form a triangle, right? But this will be mapped to a collinear point. So I'm going to just call this line L prime, right? So A is going to be mapped to A prime. So I'm going to call it, and they're going to be all collinear. So that's our assumption. And the B is going to be on the same line. So I'm going to call it the B prime. And C is going to be mapped to C prime, right? So we have transformation F. This linear transformation F sends to collinear points, right? So let's see if we can get the any contradiction out of this, right? So that's the assumption, right? So what we want to do is this, right? So since A and B are sent to the same line L prime, and this is a linear transformation. So linear transformation means that it preserves collinearity. So the AB is going to be on the same line, right? So which means that the entire line AB, so if you look at the line AB, so here, maybe I'll use a different color. Let's see here. All right, so you have a line AB, right? This is going to be mapped to L prime. So maybe I'll write it this way. So I'm going to write if you map line AB, it's going to be contained in L prime because it's going to be mapped to the same line, right? So if you take any point on line AB, it's going to be mapped to the same line L prime, right? You can say the same thing with line AC. So I'm going to just draw a line here. So the entire line AC, if you pick any points on this line, it's going to be mapped to L prime under F, right? And we can say the same thing with the line BC, right? So all three lines are going to be mapped to L prime, right? So what we want to do is, what about other points? So you have a plane, so you have other points outside of those three lines. So let's pick any random point. So this is going to be, so it's an arbitrary point. So here, so I'm going to pick a point P, right? You can actually put a point inside the triangle too. Does not matter. All right, so what we want to do is I'm going to find any interior point between A and B. So I'll probably call that guy D so that we can use postulate of Pasch. All right, so D, I'm going to just put D right here. All right, so this is my D. All right, let's look at the line BD. Right, so if you look at the line BD, I'm going to use a red line here. Right. All right, so it's gonna go. I'll go through this red line, which is BD. Right. So you can see that. So this goes through a line going through D. Right. And then if this happens to go through A or B or C, then we know that you know that you have 2 points that are mapped to line L prime. So the entire line is going to be mapped to L prime, right? So that's an easy case. But the hard case is, what if this line PD does not go through A, B, or C, right? So that's the same situation as postulate of Pasch. All right, so if that's the case, we know that it's going to either intersect AC or BD, right? So let's just say it's going to go through AC. Either way, the argument is the same. So you can see that we're going to have a point E here. Is there, right? So since we know that D is on line AB, D is going to be mapped to the line L prime. So D prime is going to be on that line, right? Since the E is sitting on the line AC, so E is going to be on the line L prime, right? So which means that the entire line PD is going to be mapped to L prime, right? So we know that, so maybe I should write that. So all three lines is going to be, so you have a AC is going to be mapped into L prime, and line BC is also mapped into L prime, right? So those are the three lines, but we picked a point outside of that. So if point P is not inside AB or AC or BC, we still could show that F of P is going to be inside L prime, right? Because here, since the entire line PD, or you can call it DE, is going to be mapped to L prime. So we know that P prime is going to be on the same line, right? So we have that. So we took care of all the points because the points are either on those three lines or outside of them, right? So which means that if you combine all those, right? So this means what? We know that we could actually map the entire plane because we look at all possible points. It's going to be squeezed into a single line L prime, all right? Do you see that this is going to be a problem because F is supposed to be onto P, so this indicates that the F is cannot be onto, right? So this is a contradiction because transformation has to be onto, right? At least. Right? So this is a contradiction. So therefore, what went wrong? So the assumption here, F does not preserve collinearity. So therefore, we know that F actually does preserve non-collinearity. All right. All right, so linear transformation by definition preserves collinearity, and this lemma actually shows that it actually preserves non-collinearity as well. All right, that's it. I hope that this was clear.